is a very complex system that communicates with the TDRS satellite constellation. And there's going to be 4 ground terminals that are interconnected via the space network, and also to TDRS. So it's probably one of the most complex systems that we've IV&V'd here. Also, this is quite a bit different system in the sense that it's not a flight system. It runs on internet. It's a network that runs on standard internet protocol. There are a lot of other protocols that are encapsulated by the internet protocol it uses. So what we're concerned about is the fault management concept for it. Now, normally on spacecraft systems in the past, we've done fault management, but relative to internal faults to the spacecraft. And so it's usually some lookup table on board the spacecraft that handles or manages the faults. In the case of SGSS, we're looking at a lot of different systems that have different features. This system is a high reliability system or a high availability system. It's a 24-hour availability kind of system. So it has to have extensive fault management. What I wanted to be able to do is show how we're going to try and assess fault management for this system as an entire system, not just part of it or a component of it. So we want to be able to sort of aggregate all of the fault management concepts that they use throughout the system. This is out of the IV&V framework in terms of reliability and fault management. So the goals are to ensure network infrastructure functions correctly. So I've replaced some of the language in the framework so that it's relevant for this particular network architecture. And so this is about network infrastructure functions, and it's about current and future space network needs. We want to ensure the architecture malfunctions and environmental conditions do not impact the functional capabilities. I wanted to have a couple of examples here where, we're talking about mistakenly seeing faults, so false alerts, fault communication dropouts due to environmental conditions. I know we've been looking for ways to identify Q2 and Q3 problems. We know how the system should function properly. We can go through the requirement spec to see what's supposed to happen. We can go through the requirement spec. In the case of this system, it's one of the first systems I've seen where they've actually put requirements in place that specify what you're required to do if it doesn't function properly. So normally you get a message request going over to another system. That message request is acknowledged. So the requirements right next door to those requirements say that you're required to detect when that message request failed, when the acknowledgement failed, and what you do when that happens. So the specification is if you get a message request or a message failure, you log the failure, you alert the operator, and you try and recover from it. So the nice part about that was it gives us our Q2 targets, specifically what you do when something fails. It also, but it doesn't cover Q3, which is phenomenology that you might find in the environment that'll give you false readings. And how do you recover from those? Those are more difficult to deal with. So there was a case of a satellite that was in space. There was an active satellite that was monitoring the ground, monitoring ignitions on the ground. I chose lightning strikes because it's less. It's another example. but what happened was it was turned on and observations began, and they all of a sudden were detecting a lot of activity on the ground. Actually, they were detecting a lot of activity below the satellite, to be specific, and they couldn't really tell whether it was on the ground or where it was. Turns out there was a meteor shower at that point in time, and it looked like there was a whole lot of lightning strikes or a whole lot of ignitions, a lot of things happening all at once, and so that wasn't expected, and so now they had to recover from that by putting in the proper software to disregard those kinds of events. Communication dropouts due to solar storms. We just had a recent emission from the sun, X-ray emission, and that has a traumatic effect on communication links also. So if you're in the middle of commanding, so that the ground terminals for TDRS command TDRS to set up communication relays. And they also download telemetry data. Well, if you have an interruption in that because of environmental conditions like storms, you have to be able to be prepared for that and counter it somehow. So those are the functional capabilities that are impacted by failure in communications, by environmental conditions. But it's challenging. I like to cite this one example of unknown, unexpected, and unpredictable events. Those events that are predictable are ones that you would expect a meteor shower to have an impact. You'd expect solar flares to have an impact. The ones that are not expected or not even thought about are the ones that are really difficult. And I had an experience many years ago where I started up my car in the parking lot, and the car literally manually shifted into gear and drove forward when I turned on the ignition. That was a surprise. What happened was they mounted the shift lever connecting rod to the transmission. They mounted it to the engine block. That year was a bad year for a 1966 Chevrolet, and the motor mounts were defective and would separate. And then when you turned on the engine, the engine itself would rise and fall. And because the rod was connected to the motor, it literally moved the rod that moved the shift lever into drive. And so sometimes you can't always predict what kind of failures you're going to have. So that was my my anecdote about reality. Commanding satellite switchover from solar power to battery power was something that I wrote an issue on, because I thought, well, when you're going through eclipse, you need to know when you're going through eclipse. Sometimes that can be unpredictable. At least a failure can be unpredictable, because you don't know if a solar flare is going to happen or something's going to happen to disrupt communication while you're trying to command the satellite to switch to battery power. And they were relying on telemetry data to indicate where they were positionally. They knew from the ephemeris data, they knew where the satellite was, and so they knew when they wanted to start and stop. But you still have the problem of, well, you still need to send script up to start the activity on the Gen 1 satellites. The Gen 2 and 3 satellites take care of themselves more so than the Gen 1. So the problem was really only with Gen 1. They don't necessarily have all the capabilities that Gen 2 and 3 have. So I wrote an issue about that, and they responded by saying, yes, we thought of that a few weeks ago, or months, or however long ago it was, but they had thought about it anyway. And so sort of validated my issue, but the issue's not an issue anymore. but it was an interesting find, because you don't always think about some of the things that can occur in space when you're looking at ground systems. But it affects you because you're trying to issue commands from the ground, and you're receiving telemetry from the ground, and you're uploading scripts based on what you know about the satellite. So that was that. That's that story about real life in SGSS. So fault management design has to support reliability and durability and durable network processing, right? IP networks, typically for a long, long time, have all the timeout mechanisms built into them so that if they don't see response or they don't find a server or a node in a certain amount of time, they just drop the data, right? That's not going to work. That's not going to work when you're in space because you're trying to communicate long distance. And that's really what this picture was trying to represent. We have to have a different kind of internet protocol that's tolerant of the distances and the locations of planets and the locations of satellites, and that'll be coming up in a future slide. It's being developed at JPL right now, that protocol. So this is the architecture. This is a very simplified architecture that I'm talking about because it involves interfaces that are prone to failure or at least interruptions in data flows. Applications, you have events that are quite frequent. And the system is large, you have a lot of events. And you have a lot of operators. You have a lot of different protocols in this architecture. They have a fault database that they can access. They have an email. It's just a complex architecture that provides all kinds of opportunities for failure. And so what we wanted to try and do is assess the probability of failure, how well they do fault management in this large and complex architecture, and so provide some sort of an assessment of how well they're working with fault management. So the architecture and services, this is a services-oriented architecture where they provide data relay services. That's the goal, that's the purpose for TDRS. Data relay services between user mocks and their own and user satellites, user platforms through TDRS, from one TDRS to another TDRS for any combination of interface when you're trying to relay data across the globe. And of course, TDRS satellites are located geosynchronously so that you can successfully perform a data relay no matter where you want to go, from a ground station to a user mock, to a user platform, up to TDRS. It just is a very complex situation, especially when you consider TDRS is geosynchronous, but the other user satellites, the other user platforms are moving around the globe. And so now you have to look for a window of opportunity to communicate with the satellite. So you've got moving objects you're trying to communicate with through fixed objects in space, through fixed objects on the ground. Everything's in motion. And then you have the interruptions in space due to solar flares, or interruptions in space due to eclipse, to objects being in the way, intrusions. So how well can it handle reliable data relay given all these complexities? So we want to look at SOA messaging reliability, services reliability, how they're specifying reliability, how they're specifying the capabilities of the system, and requirements, how it's implemented in design, and whether the code is implemented this way as well. We want to assess the compliance of the infrastructure with protocols. So we can only measure how well something is done by having a standard to measure it with. So the protocol standards is what we use to measure the goodness of their protocols that they're implementing. So we do that by inspection and by analysis. So we measure correct, consistent, predictable network behavior. A lot of this stuff is the stuff that IV&V has been doing for years in terms of making sure that requirements design are consistent, that they don't contradict other things that are going on. So if they implement a protocol, for example, from one node to another node, and then from that node to yet another node, there's a different protocol, you have protocol differences that could introduce faults also. So this is the compatibility among interfaces that I'm referring to. We want to be able to enumerate on the vulnerabilities of the protocols. Some of these vulnerabilities, in terms of data integrity, confidentiality, data availability, system availability, these are all well-known vulnerabilities and weaknesses. They're well-known reliabilities that you can find in an open forum on the internet. I ran across a requirement for managing a fault relative to the database. Right? It was writing and reading from the database, and if there's a problem with that, it was going to issue a reset. Right? The way that the language was in the requirement looked as though they were referring to a specific command given to a database. And so I downloaded the user manual, programming manual for this COTS product, and it had in it the reset command for resetting the database. I was just amazed that you have that kind of access to the technical details of how something works in a COTS product. So this is the other aspect that complicated the problem also, is that we have the requirements spelled out, we have the design written up in design documentation, but we have COTS integrated into this to the degree, well, how do you determine the reliability, dependability, the fault mechanisms that are in the COTS products? So to find the COTS products manuals online was a real treasure chest. So we used that information and to understand why the requirement said perform a reset when this happens. So we were able to tie that together. So there are a lot of complex fault management options, fault management scenarios that are invoked. And later on, I'll get to saying, well, how are we going to assess fault management on a grand scale when you have all these nodes, all these protocols, all these interfaces? What it amounts to is the initial step has to be to inventory all the different kinds of faults. You have to categorize them, bin them, and understand them. And so one of the things you do is you decide whether they've got adequate coverage for all the faults that can happen. And if they don't, you simply, you assess what the missing ones are, what the missing fault management pieces are, and you report those back to the developer. And then we'll ask the question, well, how are you going to manage this? So measuring correctness, consistency, and compatibility and enumerating vulnerabilities is all part of the inventory game. It's all part of making an accounting of where fault management lies in the system. So what's the fault management quality and reliability measures? There are some COTS products out there that actually support fault management, a lot of them. And so they're saying that you should be able to measure availability, reliability, safety, and security with your fault management product, right? So if you go and look at their fault management products, the COTS products, you see how they do it. And so my take on that is, well, if they do it that way, maybe we should do it that way too on the software that we don't have as COTS. And so that's my find on that. I want to try and leverage the way that COTS fault management products do fault management, availability assessment, reliability assessment. So that's how I'm getting the attributes, quality attributes that I need to actually assess fault management in the network, is I'm trying to leverage off of work that other folks have already done and marketed for years. You might say, well, messaging durability. Durability is a new term, relatively new term for network infrastructure. Durability has been introduced from the standpoint of the data flows have to endure the transit time, have to endure motion, planetary motion. So that's where this durability, that's the context of this durability, is they have to endure the environment. And what they have done, probably getting ahead of myself, but what they have done to do that is they do a store and forward technique on the internet protocol. The internet protocol that was developed many years ago is being revised to compensate for these long distances and time delays that impact the normal internet protocol. So they're using store and forward techniques to do that. And this is being developed at JPL, these new internet protocols that are tolerant of these kinds of mechanics. Factors that stress dependability are network latencies, data bandwidth, communication length distances, like I said before, and security threats. Today, network security threats are taking on a whole new importance. And what we've done, since we're concerned about this on this highly available system, we have a bunch of security requirements that we have to deal with as well. And so we're looking at security threats as another venue for fault management. Verification processes quantify the error handling and fault management coverage and capability. And that's what this is really about, is this is a relatively new verification process. We've been toying with how to assess or how to verify reliability, maintainability, all the LOTs for a long, long time. And it's hard to quantify all of that. And so this is an attempt at beginning to understand what it is that we're trying to quantify, what kind of fault management is there, what are the vulnerabilities and the impacts, and how fault management deals with recovery. All these things can be quantified in a database to make an assessment about error handling and fault management. We want to identify risk associated with these faults, because to identify risk is to identify impact to the overall system and infrastructure, and identify what kind of redundancies need to be built into the system to handle the risks that we've identified. Now, some of the risks that are identified were risks that are identified by virtue of looking at the COTS product specs, for example, because there are a lot of mechanisms built in to managing the reliability and risks associated with servers, hosts, platforms, and a lot of other technology. And we want to try and leverage off of that. So we're not identifying all the risk that's there. We're augmenting that risk that we identify with the risk that we see in COTS products that they have to talk about, and the risks that the developer has expressed in their requirements and design through technical interchange meetings and a number of other venues. So that's how we're going to identify risk. So all these factors for reliability, risk, fault management, handling are coming from many sources. And so we need to be able to collect them into one database so that we can get an overall picture. I like to think of this as a profile, a protocol dependability profile, a risk profile, whatever you want to call it. It's not a simple dimension. So FCAPS has been around for a long time for network management, and so a lot of these COTS products market the capability of supporting FCAPS. FCAPS is even a larger problem to assess, a larger topic to assess, or logic. So I chose to scope my problem, to faults. Configuration management, accounting in terms of user accounts and passwords and bit error rates, message error rates, performance related to how quickly something is done, how quickly startup is accomplished, how quickly messages can be responded to. So they built into their specs, the developers built into the SGSS specs, required time for responding to messages that are traveling across the infrastructure, because it's becoming a variable in this case. It's so large. So network protocols vary, so we have to account for that. Vary in their fault management capabilities. Exception handling is done, so this system has mostly Java code written for it, because it is a web services, a services-oriented architecture with web services being provided and services being provided to other users. And so now we have Java code that's involved that has built into it exception handling framework, which is handy, because there's an opportunity here for every method that you implement, you have an exception handling opportunity, for example. So these are faults. Now what I'm doing here is I'm drilling down into the core of SGSS. So now we have fault management on a application by application basis. So we not only have breadth of concern, we also have depth of concern with regard to fault management. We want to make an accounting of that as well. Now, when you have there are some challenges with Java exception framework, in that that causes the CPU, that causes the processing to escape to handle these faults and then return, and that takes time. So there's probably an opportunity to have an exception handler for every method that you call. If you did that, you'd be tied up managing exceptions. So there's a trade-off that you have to worry about. The design has to have built-in alarming, has to be able to isolate problems, run diagnostics, error handling, alerting, and error logging. They're all part of fault management. So if you want to assess fault management in this large a system, it's a multifaceted, complex endeavor. So we were fortunate to have in the requirements not only what the system should be doing, but also how it's going to recover from faults that the system exhibits. It doesn't account for solar flares, so we're going to look at that too. But it gives us very good insight into the system and how it's capable of handling all the faults. Fault management during operations. So you have fault management through development, right? So fault management through development is all about the errors that the code produces that you have to deal with. So once you have a reliable system through a reliable design, you do your unit testing, you find your errors in your code, you find the exceptions that are going to appear, so you have a head start on what to expect later on during operations. So that's what this reference to during design is all about, is making sure the design has all the built-in capabilities for fault management, and the implementation does. So then you go to operations, and you start to, because you've proven that faults are logged and alerts are given to operators, you can collect and analyze the logs that were being created. and correlating events, identification and authentication failures. Those are security-related failures. Data storage and playback capabilities allow you to run forensics because you're recording or you're archiving fault management that you're doing. So there's a lot of opportunity here to look at fault management and how well it's being done. There are protocols and frameworks associated with monitoring faults, monitoring performance. I put a couple in here. All these protocols have fault management built into them, how they're going to respond to protocol failure. There was something I came across. This has been an evolving kind of topic for me because there's just so much out there. I couldn't find everything that I wanted to find in time to put it on the slide. So I don't have a lot of the protocols here that are involved. I don't have the VPN tunneling protocol is used. The router, virtual router protocol is being used. There was something I discovered a few weeks ago called availability management framework, and I'm looking forward to investigating that to determine, well, okay, so how are they doing availability management? This is a COTS product that's trying to be developed, and a standard that's trying to be developed for availability management. So that should be an interesting read. There's a Java community process for availability management for Java. As you know, Java does its own housekeeping and is not the most reliable, it has not been the most reliable kind of thing. You couldn't rely on it taking a certain amount of time because it does it at will. You don't control when it does garbage collection, and so there's an availability problem there that I think that's been improved upon quite a bit. You have directory services that have error codes associated with not finding the entry in the directory that you're looking for. So you have to deal with that. So there's management associated with that protocol. There's error codes that get mapped to Java exceptions that are handled by the applications, and status codes. This system is built to monitor all of the errors that the system, or as many errors as they can, and to manage them. So we're looking at fault management quality and coverage, not just in LDAP directory services, but in all of the code that we see. They're employing SOAP. They get SOAP faults for the SOAP protocol that they use for services-oriented database access, web services. There's a table that's available that shows how they map SOAP faults to Java exception mapping, because now you have dissimilar fault management going on. This is the culprit here, Vint Cerf. Many of you may have heard of him. He was the co-developer of the IP protocol many years ago, 73. And he began working on interplanetary communications because he just was looking forward to what's our next challenge, right? Internet protocol has a lot of challenges with regard to getting into space and trying to employ internet protocol out there. Because they wanted to carry the web services forward into space and have planetary internet at some point in time. So the protocol has to change, has to evolve. And so they have something called a delay-tolerant network, disruption-tolerant network that they're working on. So it can deal with these disruptions. Planetary rotation, time synchronization, domain naming. So you have different domains out there. What if you can't find that domain because that server isn't available? It's rotated out of view. you have to wait for it to come around. So you run into delays for just finding an address, finding a URL. So that's what the delay tolerant network is all about, and that's really the future, and that's something that we want to examine closely to see whether they're going to employ enough fault management and fault tolerance that they need to have to meet the requirements. Manage Engine is a product out there that does FCAPs in virtual environments, which is relevant for us. That's really it. I mean, there's a lot to this subject and a lot of work to be done if we're going to properly assess fault management in this large system. So it's going to be an exciting adventure for me to try and find all the different aspects of this fault management problem. Any questions? All right.